All right, now that we know about momentum, we know about impulse, we know if our system is isolated, the total momentum is conserved, that is, the total amount of momentum doesn't change. We're ready to talk about different types of collisions. And the most important thing we want to mention here at the start is that momentum is conserved in all of the collisions that we're going to talk about here. Really, what distinguishes different types of collisions is what's happening with the kinetic energy, how the kinetic energy of the system before and after the collision compares. So keep in mind momentum before, momentum after. Here I'm using initial and final to represent before and after. The total momentum initial equals the total momentum final, and it's the kinetic energies and how they compare that is going to allow us to categorize the types of collisions. So the book lays out a few examples here. The first example is you might have before the collision just one object, and then after the collision you might end up with many objects. And so this is what the book terms an explosion, right? So from one object you get many objects. The kinetic energy feature here is that the final kinetic energy is greater than the initial kinetic energy. And you may wonder, well, where is that kinetic energy coming from? Well, there must be some potential energy stored in the system that gets transformed into kinetic energy during this explosion process. So that type of collision where we go from one object to more than one object, we would refer to as an explosion. Now, you could also have sort of the reverse of that. You could start with several objects and then have a collision and end up with just one object afterwards. And this type of collision is known as an inelastic collision. And the feature in terms of kinetic energy is that the final kinetic energy is less than the initial kinetic energy, generally speaking. And in the extreme, if the final kinetic energy is zero, that is, after the collision, all of the objects in your system are at rest, then that's referred to as perfectly inelastic. And so that's the maximum change in the kinetic energy of the system, where the final kinetic energy is zero. So again, a typical way that you would see that in a collision would be several objects coming together and then sticking together. Now, the third sort of generic type of collision would be you start with several objects that are distinct, and then there's the collision, and afterwards you still have several objects that are moving around. And so typically this would be an inelastic collision. The final kinetic energy is going to be less than the initial kinetic energy. But in the extreme, you can get the final kinetic energy equal to the initial kinetic energy. And so this is referred to as elastic. So an elastic collision is where the kinetic energy of the system is conserved. Right? So it's a very specific or extreme type of collision. Often the sort of in practice or real world example of this type of collision is billiard balls. Okay, and the next thing that we want to think about here is we want to think about the collisions that we've just talked about, but we want to think about these collisions in a more general sense than just one-dimensional collisions. We want to think beyond 1D, and really this can be extended to 3D, but I'm just going to give an example in 2D here. So conservation of momentum, if our system is isolated, then the total momentum stays the same. No matter what two times we compare the total momentum, it'll always be the same amount. But this is a vector quantity, so really this means that the total momentum in the x and the total momentum in the y direction is conserved. And so what this means in practice is that we can begin to investigate more interesting problems. And so I've got two objects in my example here, one mass of 1 kilogram moving to the right at a speed of 2 meters per second, and a 2 kilogram mass moving up with a speed of 3 meters per second. And so these two objects are going to collide and they're going to stick together. And what I want to find is the velocity after the two objects collide and stick together. Now, these objects are colliding, sticking together, so this is an inelastic collision. And so we are going to begin just by writing down what's the momentum before the collision. And that's really a two-part question. What's the momentum in the x direction? Well, that's just my mass times my velocity in the x direction, plus 2 kilogram meter per second. The plus direction is to the right. There's no x momentum associated with the other object because it's only traveling in the y direction, which means when I go to calculate the total momentum in the y direction, I only have the 3 meter per second up and the 2 kilogram mass to give me a plus 6 kilogram meter per second momentum in the y direction. And so what I'm going to do here is I'm actually going to say, all right, so that's my x and y momentum at A. I can figure out the total momentum at A just by using the Pythagorean theorem. So I'm going to do the x component squared plus the y component squared and then take the square root. That gives me 6.3 kilogram meter per second. So that's the magnitude of the momentum before the collision. And I can also get the angle just by using my trig function, my tangent function. And so I get 71.6 degrees, and that's counterclockwise from the plus x-axis. And so this is my initial momentum of my system, 6.3 kilogram meter per second, and that vector is pointing 71.6 degrees counterclockwise from the plus x-axis. Now, since my system is isolated after the collision, the total momentum actually has to equal this, right? So this is actually going to allow me to solve this problem really quickly, because after the collision, I know my two objects are stuck together, so that's a total mass of 3 kilograms, and the velocity, that's what I'm looking for. So if I multiply these two together, that's the total momentum after the collision. And the total momentum has to be equal to the total momentum in A. So that means I can immediately take this 6.3 kilogram meter per second and I can divide by the 3 kilograms. And I get that my velocity at the end after the collision is 2.1 meter per second. The direction, the exact same direction as my momentum vector before the collision. Right, the total momentum is the same before and after. Well, the only way your vector can be the same before and after is if it's pointing in the same direction and has the same magnitude. And so the velocity vector has to be pointing in that same direction as well. And so here I've used the fact that momentum has both an x and a y component, and then using the conservation of momentum, I'm able to solve for this unknown quantity. What's the velocity after the collision here? And again, this was an inelastic collision. These two stick together. All right, and the last thing that I want to go over in this video is I want to discuss a new topic that is going to be really useful for solving conservation of momentum problems, but also is going to be useful when we start to think about rotation and torque and thinking about objects in static equilibrium or in balance later on. And so this idea, the center of mass, is going to prove incredibly useful. So some collisions, the analysis can get a little bit complicated, and it turns out there are ways to simplify this if we sort of alter our approach of what we're of how we set up the problem. And so the thing I want to introduce is something known as the center of mass. And the center of mass, which I've defined here in this green box, the center of mass is a way to account for all of the objects in your system, the masses that each of them have, and the locations at which each of those masses resides in your particular problem. And so the simplest way that I can kind of present this is I've got, over here on the left, I've got two different masses, and let's say mass m is on the left, 3m is on the right, and then they're sort of connected by this massless rod. And so the way you can think about the center of mass is, where would you have to support between these two things so that the entire object was balanced, that it would just stay stationary? Now this will make a lot more sense when we start talking about torque in a few chapters, but right now just think about, if you place a support right under the middle, well, that's definitely not going to balance, because there's a 3m mass the same distance away as a 1m mass, and so this thing would not be balanced. In fact, you have to move the support closer to the more massive object, and where you would have to support represents the center of mass of the system. Now, in this case, my system is really simple. I've got two objects, and they're not moving. But the way that you calculate the center of mass is that you take into account the locations of the objects, multiply each mass by the position, add up all of those products, and then divide by the total mass. And since position factors in here, which, remember, position is arbitrary, what you call the center of mass depends on what you pick as your origin. The location right here won't change, but whether you call that plus 3 meters or minus 3 meters or plus a half meter or 0 meters, that depends on the origin of your coordinate system. So the center of mass, with this definition here, is going to allow us to think about conservation of momentum problems in a slightly different way. Now, I'll point out, this will come in handy in a couple chapters. If you, instead of having two separate discrete objects, if you had a continuous distribution of mass, you would figure out the center of mass location by evaluating an integral, right? This sum turns into an integral if you've got a continuous distribution of mass. Again, you evaluate the sum and then you divide by the total mass, or you evaluate the integral and then divide by the total mass of the system. So this is great, but we care about collisions. What if our objects are moving? Well, then you can define the velocity of the center of mass just by taking the time derivative of the position function. And so take the time derivative of this up here. That's just, well, if our mass isn't changing, then there's no need to take the time derivative with respect to the mass, and it's just the time derivative of the position vector for each individual object. And so this turns into, the center of mass velocity turns into 1 over m, and then the sum of each of the individual, look at this momentum, so it's the mass times the velocity of each individual particle. And so this is the definition of the velocity for the center of mass. And remember, these are the individual momenta of the objects in your system. And so since you're summing over all of the objects, this is actually corresponding to the total momentum of the system, and then you divide by the total mass in the system. So how does conservation of momentum come into play? Well, like I was just saying, this right here is the total momentum of the system, and so if you multiply the total mass of your system by the velocity of the center of mass, at any time that product has to be a conserved quantity, or has to be the same value. And so this can allow you to solve conservation of momentum problems in a particularly efficient manner if you are able to identify the total mass of the system and the center of mass velocity. Because once you know that that product stays the same regardless of what collisions take place, right? As long as the system is isolated, this is going to hold. And sort of a takeaway from that is that the center of mass velocity in your isolated system, that remains constant over the entire time that the system remains isolated. So if you can determine the center of mass velocity before a collision, then immediately after a collision, you know the center of mass velocity is the same thing. And that can allow you to solve the problem in a rather quick and efficient manner. Right? So you want to keep this center of mass approach handy as you're working on these conservation and momentum problems because it can allow you to solve problems approaching it slightly differently, but in a more efficient manner. Right? So now, when we meet in class, we'll be practicing solving conservation and momentum problems, both in one dimension and in two.